Okay, so I have the recorder on. Hopefully it is picking up my lovely voice. And let's get on with today's lesson, which is lesson number 2. So we had the holiday on Monday. I don't know about you all, but I thoroughly enjoyed it. And I hope everyone else here used that to get the last bit of sleep you're going to get until spring break. Okay, so I guess we'll start. No, actually, I have to wait 4 minutes. It's funny. So who has something funny that happened to them in the last 2 days they want to share with all of us? So I'm stalling right now, so 4 minutes or less. Nobody had anything funny happen to them? You didn't wake up and put the wrong socks on? Put your shoes on the wrong feet? I only have 2 feet, so when it's the wrong one, they're not even mine. You're scowling today, everybody. Be happier than that. Okay, don't be happy. Be yourself. There we're rolling in, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Still not done.
Yeah. I'm going to have to figure out a way to automatically take roll. Or not. Okay, ready for the next 2 hours of your life being flushed down the toilet in terms of Python? Good. So the topic for today is expressions. Funny ones, sad ones. And the ones I make when I'm wearing our mask. So do you stick your tongue out at people behind the mask just for the hell of it?
No, I smile at them though.
Yeah, I stick my tongue out. I make funny faces. Yeah, that's kind of a cool part of having to hide our face from ourselves. It has greatly enhanced my interactions in the retail sector because when I'm fuming at them, I can go ahead and express my fuming, and all they see is the eyes, and so nobody gets mad at each other. It's actually brilliant. It's probably as valuable to peace on this planet as the invention of air conditioning. Which was invented by whom? Not a part of this class, but just one of those interesting questions. You don't know who invented the air conditioner? Well, you got a computer. You should be able to find out.
That'd be cheating.
Try, huh?
That'd be cheating.
It would. Try searching for Willis Carrier. See if he has any association with the air conditioner. You shouldn't be allowed to enjoy it unless you know who invented it. So the toilet, as we know it, was invented by,
John Crapper.
I think it was Thomas Crapper, but the last name you got right. Okay, so today is expressions. So we're going to look at some fundamental operators, arithmetic, and simple output. But first, or wait, there's more. Let's look at the 5 fundamental computational thinking concepts which are behind all of this, which is decomposition, which is taking a complicated problem and breaking it down into simple ones and beating them into submission and then reassembling it to get the overall problem. Pattern recognition, which is to recognize patterns in things not necessarily in the same domain of interest and be able to borrow those so that we can use them in other contexts. And pattern recognition, in my opinion, is a big part of why automation works. If you can make a BMT sandwich 5-inch at Subway once, you recognize the pattern of sandwich assembly and make hundreds of them. And then if you can do that efficiently, you become a manager. You get to tell other people to make sandwiches. Abstraction, which is taking a situation and coming up with some way of modeling its most important parts, the characteristics that matter, and then isolating it from the characteristics that don't really matter, is a big deal. That's a large part of what you'll do in your remaining engineering classes is model the crap out of stuff. Algorithms are just the step-by-step instructions that we use to take those models from a conceptual idea into something concrete to make a decision. And the last part is integrating all this together into something useful. And integration normally is what ends up producing a program, and a program is a computer understandable manifestation of an algorithm. And the other stuff is there just for job security for professors like me. Okay, so the programming language we're using in this class is what? It's actually interactive Python, which is a subset of Python, but for all practical purposes, it's Python. It's a form of parcel tongue and was spoken by Harry Potter, I think, by the third book. So it was really invented by a bunch of magicians. So it's a miracle it works at all. It's an example of a high-level language. That Harry Potter stuff was BS, so don't write that down in your notes. It's an example of a high-level language. Think of the difference between high-level and low-level as uppity and pedestrian. There's also low-level languages, which are sometimes referred to as machine languages or assembly languages, although I would argue assembly is not truly low-level. Machine is. Machine language, nobody in this room can really understand. I mean, if you saw it, you'd recognize it. Oh, that's just a whole bunch of zeros and ones running across the stream. I can't even find what the delimiter is. I don't know where one statement ends and the next one begins until we run it through some kind of editor that's been taught how to separate those instructions out. So machine language looks like 001010111100 and so forth. So we have no realistic way of directly understanding it. That's okay, we don't have to, but the machines do. The next step up is assembly language. Assembly language kind of looks like what you would use in a programmable calculator. I would argue they're almost practically the same thing. So when you program your calculator, you do something like recall, and then you give a register number like register 3, recall, register true, multiply, and then you push the stack and you get an answer. So that's assembly language. The main one that some of you all will use, you computer science and computer engineering people, will probably be, is it MacASM? That's the acronym. I don't actually know what it is. I think it's for x86 processors. Assembly languages are very specific to the actual architecture. They differ for x86, ARM, Motorola stuff, and so forth. The next step up is what we would know as high-level languages. And those are languages that kind of look like languages to us. So Python, Fortran, Pascal, third letter of the alphabet, third letter of the alphabet sharp, third letter of the alphabet plus plus. Those are all what language?
C.
C. Correct, yes. Thank you for playing along, by the way. And there's a host of other ones. And they have almost natural language word assemblies that are how we program the computer. And so that is actually the attractiveness of a high-level language, is they're easy for us as human beings to read. Now, why is it important for us to be able to read them? When your car runs out of oil, what do? You have to repair it. So to repair a program, you kind of got to be able to read the underlying language. The other advantage is they're usually easier to write. So if you want to write a program that's going to add 5 numbers, divide by 5, and then report the result, which we call the mean, that's a lot easier to write in a high-level language than it would be in assembly. It wouldn't be impossible in assembly, but a lot easier to write in a high-level language. So that brings us to the whole point. The high-level languages are preferred, one, because they take less time to write for professional code. For all of us amateurs, it lets us see other people's work and steal the relevant parts for our use. They tend to be shorter and easier to read for us, and they're more likely to be correct. The second advantage or attractiveness of them is they are somewhat portable, meaning you can write if there was an ANSI standard Python, there isn't. It's not old enough to have that. But let's say there was a standard Python that was agreed upon. The closest we have right now is Python 2.7. Your Anacondas are all probably running 3.8. So if we agreed upon collectively as a community, Python 2.7 is the standard. If I wrote something in Python 2.7, got it to run on my Mickey Macintosh, I should be able to send you the file, and you run it on your Windows or your Raspberry Pi or your, I was trying to think of something that rhymes with cake, but your Celeron cake. So it's fairly hardware independent. Naturally, you would have to have a just-in-time compiler for each piece of hardware, but that's only 3 things you'd have to have using those 3 I just used as an example. It's not quite that easy yet, but it's getting close. Lower level programs, so stuff that's in assembly language, is very specific to the architecture. So if I was to get an assembly language thing running really good and was stupid enough to actually build the interface in assembly, it would run great on any piece of architecture for which it was designed. And if I sent it to someone else, someone else would curse me at least for a week as they fix the various flaws in it to make it run on a different architecture. Nevertheless, all of it's important. So that's the justification for high-level programs. Programs are run in 2 different ways. One is an interpreter. The other one is called compiled. Anyone here, I'm guessing because I don't know what your lives were like getting here, but back in grade school, which for you all would have been the 90s, is that right? You were born in the 2000s then, right? Okay, so I'm definitely an old fart here. When they first introduced, did you ever get introduced to a programming thing called BASIC? Or was it already old by then? It might have already been ancient by then. Well, so back when I started, when computers had vacuum tubes in them and you had to change the vacuum tubes frequently, although they did keep you warm on a winter day, we had BASIC, beginners, all instruction, symbolic coding language. I think that's what BASIC means. It was an interpreted language, which means each line of the file was parsed by what passed for a kernel at the time, and it attempted to execute that right then in real time. So that's what interpreted languages are. They have the advantage, like if you get that line to work, okay, cool, that part of my code works. Now you got to get the next one to work. They have a disadvantage is that it has to be converted into instructions every single time it's run. That's normally a minor disadvantage, and nowadays probably not as much as it used to be because things are faster. But it tended to be slow, especially if you're doing repetitive work, if you had something that happened over and over again. The other type of construct is a compiled language, and I think the world of compilers has more or less whittled itself down to 2-pass compilation is the industry standard. So it passes through your program code once, and it checks for syntax and other various mistakes that you can make, and it goes, oh boy, you made a mistake, I can quit work right now, and it reports your errors and stops. But if it gets through that, then it makes the second pass where it starts to assign the machine code that it's going to execute and putting the various pointers to the different variables that you've created. So that's a compiled language. You can compile it once and run it over and over again with different inputs as you supply the inputs to it. They tend to be very fast. Scientific programming languages tend to be compiled. The stuff that runs the International Space Station and keeps it skipping off the atmosphere so it doesn't come crashing and burning during New Year's and make the fireworks show downplayed are compiled languages. Python, as it's implemented to our machines, is kind of a hybrid between the two. So there's a kernel which is already compiled, and it interprets our statements and tries to run them right away. There's some parts of it that it can't, and it has to wait on it. And so that's the compiled part. But it all looks the same. You put stuff in, you press go, and either it works or we get the pink rectangle of not failure. Don't make such a value judgment yet. You've got months before you get failure in this class. The pink rectangle of encouragement. What's this encouragement? Broke. Yeah. So as a language itself, Python is formal in that it has certain requirements and certain structure. Collectively, those are called syntax. And syntax rules pertain to the tokens. What are the symbols that are used in the language? And the structures. How are those symbols organized to produce meaning? Other formal languages, hieroglyphics. So if you happen to be out in the desert and you come across a rock and it has a picture of an owl and a cat and a boat and something else, that is a formal language. I do not know what owl, cat, boat actually means in ancient Egyptian. And yeah, I'll stop with that. There are other languages in the world that are human languages that are based on characters that represent images. English, the ones that we use, doesn't do that. We have these symbols called the alphabet that when they're assembled into things called words, the words have specific conceptual meanings. Those words are tokens, so the idea is the same. We also have, in English, punctuation, commas, colons, semicolons. That's what happens when you take a perfectly good colon and you do a resection. What's left is a semicolon. That's a grotesque medical joke, but it seemed appropriate. And some of the other punctuation marks. Those themselves are also tokens, but they play a different role. They don't necessarily convey a particular intellectual concept, but they tell how to organize a sentence and interpret what each of the other tokens are. So collectively, tokens and structure are our language. So let's look at some example so that at the end of today, you will be fundamentally dangerous in linguistics. It's my goal. Consider a relativistic equation that we've probably all heard of that relates energy, mass, and the speed of light. That's E equals mc squared. So I've got it up here on the somewhere. There it is. And I've written it as the symbol E, the equal sign is a symbol, the M as another symbol, the dot as a specific symbol, and C is a symbol, and then the uppercase superscript 2 is a symbol. So I have 1, 2, 3, 4, 5, 6 tokens. And the tokens are listed there in the sentence. And then the structure is parsed or read from left to right. And if we were to try to take that simple equation that we've all seen ever since we heard about Einstein's bagels, because this is basically the bagel equation, we would interpret it as something like in the token named E, so E is just a representation of something, we want to place the result of the product of the contents of the tokens M, C, and then C again. So the operation on C is what the superscript 2 token does. It says take the value just in front of me and multiply it by itself. And then there's the dot to represent multiplication. So if we further put some human input into this and we realize the speed of light itself is a universal constant, the only things that can change in that formula are the contents of M, the mass, and similarly the contents of E, the computed energy. So there is our tokens and structure. So in that above, we had E, M, and C, which were names for things that can take on values. we'll call those variables in our programming world. Oh, it already says that right there. I guess you've probably all read ahead and you're doing the fun stuff. And then tokens equals, the dot, and the superscript 2 are symbols for particular arithmetic operations. We call them operators. And for example, the dot being a smooth curve is a smooth operator. And if I could figure out how to make this thing play music when I do stupid puns like that, I'd have the computer playing music right now. The structure of the equation itself is specific. Overall, we call the whole thing a statement. So we're making the statement that E is equal to MC squared. That's the statement. On the right side of that equal sign, the MC squared, that is called an expression in our world of Python-ness. Okay, here's my note on why you shouldn't call it your block of failure. All it means is you made a mistake. It doesn't mean you're a failure. So let's go ahead and make some mistakes just so that we can get over any sort of self-imposed value judgment. So let me see how I can... Oh, actually my computer's still working. So this morning the laptop blew chunks and I had to do it on the ones that are buried here behind lock and key. And that required me to do it in a different way than I normally would do it. But here, actually I think I'll just do it the same way because I'm fundamentally a lazy person, which is not a bad thing in a computer programming class. Laziness is good because it means you'll find an efficient way to get things done. So let me go to the remote server and log in. So this is not Anaconda. I'm doing this directly at Amazon Web Services. And hopefully I don't screw up big time and make a terrible mistake. So I will go ahead and I'm going to bring myself a launcher. And I want to make a Python notebook. And that is... Okay, so here's a good quiz question. An empty notebook or a full notebook? Easy question. That's an empty notebook. By default, I've programmed it to open up with a code cell and with the cryptic name Untitled1. And why is it called Untitled1? Because there's already an Untitled in this particular file system. So that is a code cell. If I execute the code cell with a comment statement in it, nothing happens. All right, so I had a reason for doing that, and it wasn't just to waste time. Let's copy that script into the code cell. So all I did was press the copy paste on my computer, and I've now populated the code cell with the comment that says clear all variables and then do the example. And I did not leave the script for how to clear a notebook. So that's probably what it should look like, is right there. So what do you think will happen when I execute that cell? Yes, since we're talking about the box of failure, we'll get the box of failure. We better get the box of failure. Sure enough, we have failed. Okay, cool. So now that's the right attitude for failure. Yeah. Let's see what we can do to deal with that failure. We have a choice. We can quit right now and just walk over that way to the business school and have a very successful career. Or we can take this as an engineer and says, even though I want to make a lot of money and I like money, being a business person sounds utterly boring and painful to me. So we'll take the engineering approach, at least today. So what is the message that it is telling us? You can read it right there. It says, mass is not defined. So your best guess, what does that mean to you?
The variable mass isn't defined.
Yeah, it exists, but it has no value. So I say we give it a value. We can give it the value that is here, which I think we'll do because I'm lazy, or we give it any value we want. You'll notice I inserted a line and I'm putting the definition of mass before the statement. Remind me when we get to the end of this in about 2 or 3 minutes to do the opposite of that to show you why. Dang it, we're still failures. However, we're a different kind of failure now. What kind are we now? Yeah, we haven't defined a value for the speed of light. So let's go ahead and do that. Where's my speed of light? There it is. It's pretty fast light. That's a lot of meters per second. And just for fun, I'm going to put it after the statement. I think I'll be a failure one more time, but in this case I'm doing it on purpose. Things have to be defined before they can be used. In this case,
so the other 2 times weren't on purpose.
yeah, no, those are just typical. So that brings an important note. So these things execute from the top down, and you notice it's keeping a counter here. That's the 4th time we've attempted to execute that entire cell. And so if you have a 4 up here and a 1 down here, that happens from time to time. You've got them out of order. You haven't broken anything. Your solution at that point is to give up and go to the business school, or just run all the cells and it will start at the top and work its way down. Usually get the sequence correct. Okay, so now we have, I hope, fixed this. And sure enough, we didn't get the pink screen of failure, but what's the energy? Oh, it knows. It's sitting there in the kernel somewhere, probably having fried chicken with Mr. Sanders. We have to issue the instruction. Well, now that you've done all that work for me, go ahead and tell me what you found. And so we'll use the print function, which is built in. And there's what the function looks like. So it's the keyword print. I suggest you don't ever name a variable print because it probably won't let you. And even if it did, it would get very confusing. And there's a few other reserved words that you can't use for variables. And the editor shouldn't allow it. I mean, it'll let you type it because its purpose is to make you waste your life, but it won't actually function. So we have print in parentheses, and then we have to tell it what to print. So what do we want to print? Yeah, we want to print the energy, which is cap ENERGY. And I'll just put the name there. So what it will do when it sees that is, okay, you want me to print this object. The object's named energy. I'll go into whatever is in energy, and I'll pull the stuff out there, and I'll make my best attempt to represent it to the output console, and we get the energy right there. That's a whole bunch of numbers, and the units of that would be, let's see, mass is kilograms, speed, kilograms, meters, kilogram meters squared per second squared. So you got a kilogram meter, which is a newton. So you have newtons per second, newton meters per second, which is a unit of energy. So it's easier to do it if you write it out on a piece of paper, but that's a lot of newton meters. So it doesn't take much to get your planetary rail gun out and make it all the way to season 6 of The Expanse. Okay, so let's return to our lesson. How am I for time? Pretty good. Okay, so now we got our script running without errors, and we can get even fancier. In the print statement, in this example up here on the screen, we've not only told it the contents of what to print, we've wrapped some strings around it to make the number look meaningful. And we get, I can't even do that, 89 Newton meters, a bunch of Newton meters. If those were pennies, I would be happy. I also wouldn't be standing in front of you because I could pay somebody to do this and sit there in my lazy chair living up to its name. So let's look at our program we just wrote. What are the tokens? What are the tokens that take on values? Anyone? Mass, good. Speed of light, good. Yeah, agreed. What are the tokens that represent operations? Asterisk, asterisk, 2. Someone said that over there quietly because they weren't sure they were right. You had it right. The equal sign. The single asterisk for multiplication. Good. I think you've all got it. So let's get on with the story here. So in that prior example, we had tokens that took on values, and those values could change depending on the inputs. Critters like that are called variables, not to be confused with constants, which look almost the same, but they don't change. Variables are names given to data that we want to store, manipulate, and change in programs. Variable has a name and a value. So it has whatever its name is, it also has a value. The value representation depends on the type of object or whether the variable is an integer, a real number, also known as a float, a character string, known as a string. There's a few other types too, but those are the big three when we're getting started. If you already know this stuff, just pretend to stay awake. And the utility of these variables comes when we have a structure like E equals mc squared, and we already know that, but we want to be able to supply different inputs and get different outputs. At that point, it would be stupid to write energy 1 equals 1 million kilograms times 290,000 meters per second times 290,000 meters per second, and then change the numbers every time. It'd be a whole lot easier if we had a list of those different numbers and we just fed it to the expression over and over again. So suppose we wanted to store the time of concentration for a hydrologic calculation. You don't even have to know what a hydrologic calculation is. You do know what the word calculation is because you've been doing it in other classes. And so we'll name the variable time of concentration, and then we assign a value to the variable. For instance, time of concentration equals 0.0. After that assignment is executed, the variable name is time of concentration, in this case all one word. The value of the variable is 0.0, and that decimal point also in the initial assignment also tells it that that is going to be treated as a real or a floating point object. If we didn't have the decimal point, if we just put time of concentration equals 0, on initialization, it would turn it into an integer. Now later on, we could easily divide it by 1 and assign it back to itself, and that would turn it into a float, because division almost always produces floating output. So like everything, we have to have rules. So these are naming rules. So variable names in Pythons can only contain letters A through Z and cap A through cap Z, at least in English. I'm sure there are versions in other languages that incorporate symbols of those other languages. In the case of hieroglyphics, it can contain the symbols owl through chicken and various other symbols and hieroglyphs. They don't have canoes, but they do have longboats. So. And the numerals 0 through 9, or the underscore. The first character can't be a number. If it is, it won't work correctly. Otherwise, you have considerable freedom in naming. Because you have 26 lowercase letters, 26 uppercase letters. I don't know how long a variable can be, but it can be plenty long. You don't have to do it like in the olden days of vacuum tube computers. When I was sitting in the very position you were, not in this room, I was in a different country, California, a different state, a long time ago, when dinosaurs roamed the earth. We were limited to, I believe we had 6 characters, which was what a variable could be. So if you find code from the 1980s, they'll have goofy looking variable names because somebody's trying to condense a fairly long idea into 6 characters. The names themselves can be plenty long. So for example, runtime run underscore time, underscore run time 2, and underscore 2 runtime are all valid variable names. But if you had 2 runtime, I don't know why you come up with a name like that. I must have been interested in 2s and runtimes at the time I wrote this. That's not valid and will create an error when you try to use it. So let me go ahead and grab these and I'll explain what that type function is. So we will go here. So first we have the variable named runtime. We'll set it equal to 1 decimal point. What kind of variable is that going to be? Integer, string, or float? Float, good. 2 runtime equals underscore 2 runtime equals 2. Integer, string, float. Someone said integer. There you go. You're getting there. I don't have a big pink box of failure. I think I ought to print one and put it on foam core so I can bring it to class, because that would be a pretty cool sight gag, especially when the reviewers are logging in on the camera watching me teach. Runtime 2 equals 2, integer, string, or float. It's actually still an integer. There is a function named type, and what the type function will do is it attempts to return the type of object that you put in the argument or the parameter list. So in the case of variables, the kind of types we'll get back are integer, string, float, boolean. There's a few others. And actually it's going to tell us that those are all class objects. So when we run it, we do that, and we have a classy float, a classy integer, and a classy integer. Now watch what happens when I do that. So all I did was take the underscore off of the leading character on 2 runtime, and I'm now a failure again. And I'm the worst kind because I'm an invalid syntax. So I've paid a tax and they're not even taking my money. I hate it when that happens. We can fix that by just putting underscore that back and continuing. We have enough time. Let's have a teensy bit of fun. Whoever's chuckling, he's got a weird way of having fun. Agreed. Agreed. Let's see if I remember how to do this. I might have to look it up. I am going to have to look. I was actually going to try to get the memory address of each of the variables, but I forget the sequence to do that. What I was going to attempt to show, and I'll just tell you, and you're going to have to trust me until you can do it yourself, is that runtime 2 and underscore runtime 2, which we, the human beings, think are different variables, actually are internally represented as the same location in memory. It's really frickin' bizarre. So keep that in mind when stuff doesn't quite operate the way you want. And the reason it does that is we assigned it to this 2, which was interpreted as a literal constant 2. So the 2 was never converted into a number. It was a literal constant, and that gets a place in memory, and then it is established a pointer between these 2 values and that particular 2. I will avoid doing that to you on tests and homework because it's really confusing. Most of the time everything works out just fine. But when stuff starts to not make sense quickly, it's worth looking into how to actually get the addresses of the variables. I think there's a lab assignment where that gets demonstrated. All right, there are some reserved words that are not used as variable names because they have pre-assigned meaning in parcel tongue. Why do you think I typed the word parcel tongue? I am old. Damn. That was the language that Harry Potter spoke to the basilisk, which was a snake, which is a big-ass old python, and I thought that would have been a cute thing there and get everybody all motivated into it. I guess not. They have pre-assigned meaning in Python. These words are print, input, if, while, for, and there's quite a few others. There's probably 30 reserved words. The interpreter won't allow you to use them as variables, and it will issue an error message when you attempt to run a program with such words used as variables, or as we have now established, the failure message, the error failure message. Our next thing are operators. So the equal sign that we've used in the variable definition is called an assignment operator, or the assignment sign. The symbol means that the expression to the right of the symbol is to be evaluated, if it can be evaluated. If it can't be evaluated, what do we get? We get the loser box. Yeah, the failure box. I like loser box.
Spelled from failure to loser.
Yeah, we might as well do the whole spectrum before the end of class. So the pink box of encouragement. But if it doesn't return an error, then it evaluated to something. It most likely either produced a string, an integer, or a float, or possibly a Boolean. And it will take that and stick it into what's on the left of the equal sign, assuming what's on the left of the equal sign is an object that can accept an input. So for example, we have a statement there that says x equals 5. So what is contained in the variable named x after that particular statement's executed? 5. Good. Y equals 10. What's in 10? What's in y? 10. Good. And if we print those two, if we print x comma y, it's going to print the contents of x first, then the contents of y. You notice we wrote it as x comma y. If you expected the actual comma to appear in the print statement, you have to explicitly provide that as a character. So it's going to print the 5 and then the 10. If we now make an assignment y equals x, so what y equals x is telling our computer, take the contents of x, put it in y, and don't change the contents of x. Just reach into x, take what's there, make a copy of it, and then stick it into y. What's in y is clobbered, it's gone, it's destroyed, it's history. Unless it's your personally identifiable information, in which case it shows up on Vladimir Putin's desk tomorrow morning. So it takes the 5, it shoves the 10 out of the way, and leaves the 5 behind. So now when we print the two variables x and y, what do we get? 5 and 5. So it's not, at this level, it's not too complicated. When we assign the values, so that's all written words for what we just said out loud. Here's a list of the arithmetic operators. The first one is assignment, the equal sign. Addition, it chose to use the plus sign. Damned if I know why. Subtraction, minus sign. Again, confusing. Multiplication, the asterisk. That's because if you used a small x, you would be confusing that with a variable name. That would screw things up. Division is the single division symbol. And so x divided by y would divide the value in x by the value in y. If there was fractional result from that division, it stores the result as a float. If we have floor division, which is two of those divide by symbols right next to each other, and that's what separates the operands, x divide by y is divide x by y and truncate the fractional part of the result. So if x is 3 and y is 2, what would floor division of 3 divide by 2 give us? I claim it'll give us a 1, but let's check that. So 3, do 3 divide by 2 first. That gives us 1 and 1.5 as expected. Floor division, we get the 1, the 0.5 was truncated. Truncated is the high-level word for throw that thing away. Another type of division is called the modulus, and what this does is it finds the remainder in the division. So in that prior one where we had 3 divided by 2 in old-fashioned kindergarten level arithmetic, 3 goes into 2 once with a remainder of 1. So the modulo 3, modulo 2 should produce, hope it produces a 1. I always have to do what I'm doing right now every time I need to use it. Sure enough, there's a remainder of 1. If we go 3 into itself, that should produce a value of 1. What's the remainder? There is none. Correct. If we go 3 into 1, that'll go in once with a remainder of 2. Or maybe not. Okay, well, never mind.
Just ignore that.
Just ignore that last one. The modulo is used a lot when you're doing repetitive things, and say every 1,000 repetitions you want to generate output. You have the modulo function of the counter divided by 1,000, and when that modulo hits 0, you're at a whole 1,000 count, and you just spit the output that way. That's a good use of the modulo function. Also can be used to tell if things actually divide each other completely, if you're looking for prime numbers or even numbers or odd numbers.
That last example be on the test.
The only ones that work. Exponentiation is 2 asterisks right next to each other. So x asterisk asterisk y raises the value in x by the value in y. And then there's these ones which to me are kind of goofy, but they are somewhat modern versions. I call them additive assignment, subtractive assignment, multiplicative, and division assignment. They save like 1 character when you're typing code, but they're stolen from C, because I think the C programming construct uses this extensively. So for example, x plus equals 2 means take the current contents of x, add 2 to it, put the result of that addition back into x, continue. So x plus equals 2 is equivalent to x equals x plus 2. X minus equals 2 is x equals x minus 2. I personally don't see the typing savings of this particular construct. So I think this is actually an ancient form of obfuscation, which is to make code hard for amateurs to read so as to preserve the earning power of professionals. Nevertheless, you'll see it when you're stealing other people's code in this class, so you might as well know what it's doing. So we can run this script right here and look at what a bunch of different arithmetic operators are. We set x to 10, y to 5. We print them, we add them together and print it. We subtract them, print that result. Multiply them, print that result. Divide them, print that result. Add 1 to x, and then floor divide y, and so on. You can see the results right there. There's no point really running that. The additive assignment, there's examples of each of those right here. Again, straightforward. And then because I'm sort of anal on variable typing, because that's coming up our next lesson, when I'm printing, I'm actually printing the object type and then its value. So for example, this first one is going to be integer, and let's see, 1 plus 2 is 3. Sure enough, I can still do arithmetic if I keep it simple enough. So we get to the end, which is expressions. Expressions are the algebraic constructs that are evaluated to get placed into a variable. So the things to the right of the equal sign in that particular line there, this is x1 equals 7 plus 3 times 6 divided by 2 minus 1. The 7 plus 3 times 6 divided by 2 minus 1 is the expression. And it's evaluated left to right usually, and I've tried to convert it into words. By the way, just in passing, that's a terrible way to create that particular expression, because there's a lot going on that you are depending on the default behavior of the system to do for you. It'd be a whole lot better if you group things to make the arithmetic do what you expect, because sometimes you can get stuff that you don't expect. So working from left to right, the first thing is that it has integer 7, and then it sees the 3, and then it sees the multiplication symbol. So it immediately knows I have to do something else. And so the usual precedence is division, multiplication, exponentiation, division, multiplication, addition, subtraction. So it's going to take that integer 6, divide by an integer 2. The result of that division is the float 3, because division almost always produces floats. And then we're going to multiply the integer 3 by the float 3, and we get a 9, but it happens to be a float. From that 9, we subtract a 1. So the result is an 8, which is a float. And then we add the integer 7 to that floating 8, and the result of that is 15, and it's a float. So if we were to run those expressions, we would get, well, let's go ahead and run the example because we've got 2 minutes or less to go. Actually, the timing worked out pretty good. Okay, so we'll run the example. Shift Enter, and we got the it's because I have floor division. Let me put back the original case. Floating point 15, as expected, and if we change this from floating division to integer division, so 6 divided by 2 is 3, the remainder of 0. And do that, there's no reason for it to have to type convert, and we get the expected result is an integer. And I think that's where we stop for today. Yes, so to summarize in 1 minute or less. Okay, so far in our story, I keep mentioning computational thinking as a problem-solving technique leading to an algorithm, namely because that's the title of the class. The tool to implement the algorithm is the program, in our case, Jupyter Lab running a Python kernel. And as a formal language, we introduce token and structure. And actually, more importantly, none of us are ashamed of getting the pink screen of abject failure and loserness. It's going to happen. Deal with it. And don't walk over to business school. You're all too good for that. We created some simple scripts that had intentional errors and saw what the errors are. So as you're starting out, if any of you are starting out, I mean, some of you have probably done a lot of this already, either in Python or another language, and are comfortable with that, you're going to make mistakes. Don't get all torqued about them. Read the error message. Don't see the red box and go, oh shit, and try to fix stuff. Read the error message. Usually at the bottom, the last part of the message is the most diagnostic. Now, when you get really dramatically good errors, and it has to do a trace back through 5 or 6 different function calls, those are unintelligible. Those tend to be not quite useless, but they're approaching useless. But these kind of ones, you can read the error and usually make sense out of what's wrong. And as an added bonus feature, let me make the error again. On the simple ones, it's kind of telling you where it thinks the error is. So that little caret, that up arrow symbol at between the 2 and the R is kind of locating where it encountered the error and stopped executing and started doing its whole exception printing stream. When you get the complicated one, this red box can take a page or two of the screen up, and you're scrolling down and you're looking for an English-like looking word to see if you can figure out what's wrong. Those are admittedly quite a bit harder to fix, and sometimes I just disable that entire piece of the code and try to get it working one bit at a time. This error correction is just a part of the job. And at some point, it's not really fun, but it's just something you got to do. So get accustomed to it. Any questions? Cool. I will see you all in lab in about 10 minutes. It should be the same Zoom link, but I will attempt to send an email to everybody.
I had a question. So in my ES1 homework, When I changed the cell from Markdown back to code and then back to Markdown, the image like disappears and comes up in a little box, and you can't see what it is.
Okay. It's because it can't find it.
Okay.
So the image needs to be in the same directory structure as the sheet. So when it happens to me, especially if all you did was change cell type, close that notebook, and then just reopen it.
Okay.
And usually that'll pick up the